Okay, let's unpack this. When most people hear Ice Age, they picture this one single block of time.
Right, a deep freeze.
Exactly, a deep freeze that just happened once, a long time ago, maybe with a few woolly mammoths shivering somewhere. But that term,
Yeah,
it just glosses over the incredible complexity of what was actually happening.
it really does. Because what we call the Ice Age isn't a single event at all. It's actually a whole series of cold and warm phases, part of this huge ongoing cycle.
And that's what we're diving into today. We're looking at the most recent, and you could argue the most influential, of those cold spells, the last glacial period, or the LGP.
Yeah.
So our mission today is to cut through some of that confusing terminology and really show you how the LGP, it spanned from about 115,000 years ago down to around 11,700 years ago.
Covering most of the late Pleistocene.
Right, how it didn't just, cool the planet,
Yeah.
completely restructured continents, it redirected massive rivers, and it basically set the biological stage for all of human history.
And that framing is so crucial to understand. The LGP wasn't just Earth's freezer switch getting flipped on. It's just the latest chapter in a much, much bigger story.
The ongoing quaternary glaciation.
Exactly. This bigger ice age started, around 2.5, maybe 2.6 million years ago. That's when the Arctic ice cap first started to form. And ever since then, it's just been this back and forth.
Between the cold phases where the ice advances, the glacials, and then the warmer phases where it retreats, the interglacial. And if you're wondering, what kind of clock is the Earth running on to drive these huge climate swings, the answer is actually not on our planet at all.
That's right. The fundamental pacing mechanism for all of this is astronomical. It's these periodic, totally predictable variations in Earth's orbit.
The Milankovitch cycle.
Milankovitch cycles.
We're talking about three main things here, right? The tilt of the axis.
Yep. Obliquity.
The shape of the orbit, which gets more or less oval.
Eccentricity.
And then that slow wobble of the axis like a spinning top.
Precession. That's it. And they're tiny shifts, really, but they change how much solar energy hits the high latitudes, especially in the summer. And that's the key.
Okay, that's kind of counterintuitive. I'd think it would be about cold winters.
You think so, but the theory is that ice ages really kick off when the summers are just too cool to melt the previous winter's snow. So you start getting accumulation year after year.
And the ice sheet starts to grow.
And as it grows, it's bright white, so it reflects more sunlight back into space, which cools the planet even more. It's a self-reinforcing feedback loop.
So within this long LGP timeline, there was a point of maximum cold, right? The absolute peak of all this.
Yes, the last glacial maximum, or LGM. The sources are pretty clear. This happened between about 26,000 and 20,000 years ago.
And at the LGM, you just had these vast regions buried under ice. I mean, in Canada, the ice was, nearly 2 miles thick.
In some places, yeah. It was a time of just immense environmental stress globally. It completely changed the rules for where and how life could even survive.
Okay, so here's our first big aha moment for you, right at the top. The end of the LGP is not the end of the Ice Age.
That's such a critical misconception. If you define an ice age geologically as a time with permanent ice near both poles, then we're still in one.
Because we still have Antarctica and Greenland.
Exactly. We are currently living in the Holocene epoch, which is just the latest warm interglacial phase within that much longer Quaternary ice age. Geologically speaking, we're just, enjoying a temporary thaw.
Makes you wonder what the next turn of that Milankovitch cycle might bring.
Yeah.
But for now, let's get into the consequences of that last big freeze.
Okay, so if we're going to synthesize the environment of the LGP, especially during the LGM, the biggest, most dramatic effect was the drop in global sea level.
And we're not talking a few feet. It was profound. The ocean surface was, up to 120 meters lower? That's almost 400 feet.
It is. All that water was just locked up on land in these colossal ice sheets. And when you expose that much continental shelf, you create land bridges.
And the most famous one has to be the Bering Land Bridge, Beringia connecting Siberia and Alaska.
That's the one.
I find this so fascinating because it wasn't just some narrow little strip of land. It was a huge, cold, dry plain, thousands of miles wide.
A whole subcontinent, really.
And it was the highway for mammals, for bison and horses, and of course for the first people moving from Asia into North America.
The timing of that bridge just fundamentally altered the landscape of two continents, both biologically and for humans. I mean, think about the ambition of that, crossing this exposed landscape into a completely new world, all because of a sea level drop caused by ice thousands of miles away.
But the period didn't just gently warm up into our modern era. It ended with a shock, right? A kind of a return to glacial conditions.
A massive climate hiccup. It was called the Younger Dryas. It starts around 12,800 years ago, and temperatures in the northern hemisphere just plunged right back towards glacial levels.
What caused that?
The leading theory is a disruption to the big ocean conveyor belt, the Atlantic meridional overturning circulation, probably from a massive pulse of freshwater melt coming off the retreating ice sheets.
So the very thing that was ending the Ice Age, the meltwater, actually slammed the brakes on the warming and sent things back into a deep freeze for a bit.
For over 1,000 years, yeah. It was like Earth's final shiver before settling into the warmth of the Holocene. And the sharp warming that ended the Younger Dryas around 11,700 years ago, that's the official finish line. That's the end of the LGP in the Pleistocene.
And that transition, it wasn't just about geography, it was huge for biology. We're talking about the mass extinction of megafauna.
And what's fascinating here is the timing. This late Pleistocene period coincides almost perfectly with the extinction of all these big, charismatic animals.
Yeah.
You know, the woolly mammoth, the giant ground sloth.
Saber-toothed cat, the Irish elk.
All of them. And it happens pretty rapidly, just after the LGM. And the timeline lines up broadly with the arrival of modern humans on these continents.
Which has led to one of the biggest debates in this whole field.
Oh, absolutely. It's basically climate stress versus the overkill hypothesis.
So on one side, you have the idea that as the climate warmed up and the habitats changed so quickly, these specialized big animals just couldn't adapt fast enough.
That's the climate argument. But then you have the overkill hypothesis, which basically says, well, we did it. As highly skilled human hunters moved into these pristine ecosystems, the local megafauna who had never seen predators like us were just wiped out.
So where do the sources land on this? Is it one or the other?
It's almost certainly both. It's an interaction. The climate change put the stress on the populations, made them smaller, more vulnerable.
And then human hunting pressure was the final blow.
Exactly. The LGP really set the stage for one of the biggest ecological turnovers in recent Earth history.
Okay, before we dive into the specific ice sheets, we have to talk about the terminology. It's a bit of a headache. If you're trying to read about the LGP, you see all these different local names.
It's confusing, but necessary. The cooling was global, but the local effects were different everywhere. So geologists just named the period based on where they were studying the evidence.
Right. So in North America, you'd be talking about the Wisconsin glaciation?
That's the one that covers the huge Laurentide ice sheet.
But then if you hop across the Atlantic to the British Isles, it's the Devengian.
Yep. And then in Northern Europe, Scandinavia, Germany, Russia, you're looking at the Weichselian or Vistulyan glaciation.
And in the Alps, where so much of this research started, it's the Würm glaciation.
Exactly. And they all behaved a little differently. The Würm in the Alps was very different from the massive Weichselian sheet that covered the plains. It just highlights how specific the local evidence really is.
So let's zoom in on those giants now, the Northern Hemisphere ice sheets. This is where the LGP physically carved the world we see today.
And we have to start in North America with the absolute behemoth, the Laurentide ice sheet. It just smothered most of Canada and pushed way down into the northern U.S.
It's hard to even picture the scale. At its thickest point, it was 3 kilometers high, taller than any mountain east of the Rockies. That's the Wisconsin glaciation.
And while the Laurentide covered almost everything, there's this weird anomaly. Alaska and the Yukon were mostly ice-free.
Which seems so backwards. The land closest to the pole didn't get buried.
It's all about aridity. It was just too cold and dry. Cold air can't hold much moisture, and the huge ice sheets to the south and east blocked any moisture coming in from the Pacific. So not enough snow to build a glacier.
And that ice-free corridor, Beringia, was critical.
Absolutely. Now, the Wisconsin glaciation wasn't just sitting there. It was like a colossal bulldozer, totally changing the geography south of the ice.
Yeah, if you live anywhere north of the Ohio River or you've been to the Great Lakes, you're looking at a landscape sculpted by the LGP.
Here's where it gets really cool. The Great Lakes. The ice sheet didn't just create them. It took old river valleys and just scoured them out deeper and wider.
Like the world's biggest piece of sandpaper.
Exactly. And then when the ice retreated, those massive basins it carved just filled up with meltwater.
And the ice was so heavy it actually pushed the land down. And that land is still rising today, right? Isostatic rebound?
Still rising, and it's actually causing the Great Lakes to slowly tilt and drain southward.
Wow. And it didn't just make lakes, it rerouted entire river systems. The Ohio River, as we know it, is a product of the ice blocking an older, bigger river, the Tees River.
Even Niagara Falls is a feature of the retreat.
What about the East Coast?
If you've ever been to Cape Cod, Long Island, Martha's Vineyard. You've been to the edge of the glacier.
You mean the terminal moraines?
Exactly. The ice sheet was like a giant conveyor belt carrying rock and dirt. And where it stopped advancing, it just dumped all that debris in these huge ridges.
So those beautiful islands are basically just glacial garbage dumps.
The most scenic garbage dumps in the world, yeah.
Okay, let's head west. The other big one in North America was the Cordilleran ice sheet over the Rockies.
And this is where we get one of the most spectacular cataclysmic events of the entire period. Glacial Lake Missoula.
Okay, this is an incredible story. So there was this enormous lake.
In what's now western Montana, yeah. It was dammed up by a big lobe of ice from the Cordilleran sheet. It held about half the water of modern Lake Michigan. Just a ticking time bomb made of ice and water.
And when that dam broke,
it didn't just leak, it unleashed a biblical flood, the Missoula floods. We are talking about a wall of water moving at 60 miles per hour, scouring eastern Washington. The flow is estimated at 10 times the flow of all the rivers in the world combined.
10 times.
The evidence it left behind, the channeled scablands, is just staggering. It carved deep canyons into solid bedrock, created huge dry waterfalls.
Wow.
You can still see these massive ripple marks in the landscape today, some of them 50 feet high.
And the craziest part is that this wasn't a one-time thing.
No. This cycle, the lake forming, the dam breaking, the cataclysmic flood, and the lake reforming, it happened about 40 times.
40 times over 2,000 years. That's just mind-blowing.
It's one of the most powerful demonstrations of the raw power of deglaciation you can possibly imagine.
Okay, so let's cross the Arctic now over to Eurasia and the Waxilian glaciation.
This was Europe's equivalent of the Laurentide. The Scandinavian ice sheet was immense. It covered all of Scandinavia, pushed into Britain, Germany, Poland, Russia.
And because of that ice and the low sea levels, a lot of the North Sea was dry land, right? The famous Doggerland.
Exactly, which connected Britain to the continent.
And in the Alps, we had the Würm glaciation. How was that different?
The Würm was more about big valley glaciers and smaller ice caps. It wasn't one single massive continental sheet. But it was still incredibly powerful. It basically scraped away almost all the evidence of earlier, even bigger glaciations.
But maybe the most complicated story from the European retreat is the birth of the Baltic Sea.
Oh, it's a geological melodrama. The Baltic we know today is actually really young, only about 4,000 years old in its current state. Its formation is this wild four-stage process of the land rising and the sea level changing.
Okay, so walk us through it. Stage one, as the ice is melting.
The land is pushed down by the ice, so meltwater pools in the basin, but a connection to the ocean opens up, and you get a temporary saltwater body called the Yoldia Sea.
Saltwater, okay. But then the land starts to rebound.
Dramatically, the land rises up, and it actually cuts off that connection to the Atlantic. So now the basin is isolated, and it fills up with fresh water from all the continued melt. It becomes the huge freshwater Ancillus Lake.
But the story isn't over.
Not at all. Because while the land is rising locally, global sea levels are rising everywhere, and eventually the ocean rises high enough to breach the sill again.
And it becomes saltwater once more.
It becomes the Littorina Sea. And from there, it slowly evolves into the brackish system we have today. It's a perfect example of this tug-of-war between local land uplift and global sea level rise.
It's so easy to just focus on North America and Europe. But let's shift to the global periphery, from the tundra to, believe it or not, the tropics.
And right away, we see huge contrasts. While Scandinavia was buried, northeastern Siberia was mostly not covered by a big ice sheet.
Again, because it was too dry.
Exactly, too arid. So instead of a massive sheet, you had these restricted ice field complexes just covering the mountain ranges. It shows you it wasn't just uniform cold everywhere. It was a mosaic of cold and dry or cold and wet.
What about further south, in Asia's high mountains?
The Himalayas, the Tibetan Plateau, we definitely see evidence of major glacier advances there, but there's a big debate about whether it was one single massive ice sheet covering the whole plateau or just a lot of really big but separate mountain glaciers.
And the current thinking leans towards
Complex, localized glaciation, but the jury is still out on that one.
But the truly surprising thing is how close to the equator you find ice.
As long as you have the altitude, you can get glaciers anywhere. We see evidence in Taiwan and the Japanese Alps.
And in Africa.
Yep. Glaciers in the High Atlas in Morocco, and a pretty substantial ice cap, several hundred square kilometers covering the big East African mountains, Kilimanjaro, Mount Kenya, the Rimzoris.
Okay, let's pivot to the southern hemisphere. Glaciation was less extensive down there, but still pretty profound.
Antarctica, of course, was completely glaciated. But there's a weird counterintuitive detail from the ice models. They suggest that the ice over central East Antarctica was actually thinner during the LGP than it is today.
Thinner? How is that possible?
Again, moisture deprivation. Changes in atmospheric patterns basically starved it of snowfall. It really challenges that simple idea that the LGP just meant more ice everywhere.
And in South America, it was all about the Patagonian ice sheet.
Correct. It ran down the spine of the Andes, and you see this amazing contrast within the ice sheet itself. The western side, facing the Pacific, got tons of moisture, so it had wet basal conditions. The ice was sliding on a layer of meltwater, moving fast, carving aggressively.
While the eastern side was in the rain shadow.
So it was cold-based. The ice was frozen solid to the ground, moving much, much slower. It just shows you how local climate dictated how the glacier behaved.
And we even find tropical ice down there, too, in New Guinea.
We do. Mount Gilu had an ice cap covering about 188 square kilometers. And to maintain that, you needed temperatures about 5 to 6 degrees Celsius colder than today.
Okay, we have to end this section with this really important debate about glaciation in southern Africa, because it really highlights how tricky this all is.
It raises such a great question. How much can local evidence on the ground contradict these big global climate models? We know there were small glaciers in the Lesotho highlands in sheltered spots, but the idea of widespread glaciation is really debated.
Why? What's the argument against it?
Well, the geology. For one, there's a lack of classic glacial features, things that show the ice was moving and scraping. The big one is something called roche-moutonnées.
Sheep rocks.
Literally sheep rocks, yeah. It's a rock formation that's been smoothed on the side the glacier came from and plucked rough on the other side. It's the signature of a huge scrape. And the argument is those are mostly missing.
And that ties into a climate puzzle.
It does, because to get widespread ice there, you would have needed a temperature drop of 10 to 17 degrees Celsius. And a lot of researchers think that's just climatically implausible for that latitude. So the thinking is it was probably an arid periglacial environment, cold and freezing, but without huge active glaciers.
So as fascinating as the ice itself was, we need to talk about what happened when it melted. The ongoing legacy.
The first and most obvious one is that process we keep coming back to, post-glacial isostatic rebound. The Earth is literally springing back into shape now that the colossal weight of the ice is gone.
How fast is it happening today?
It's surprisingly fast. In parts of Scandinavia, northern Sweden, and Finland, the land is still rising by as much as 8 to 9 millimeters a year.
Wow, that's almost a meter a century.
It is. And for you, the learner, this is a huge deal for archaeology.
How so?
Because ancient Stone Age coastal sites, villages that were right on the shore 8,000 years ago, are now miles inland. Archaeologists can literally date these sites based on how far they are from the current shore. The land itself is a clock.
That's incredible. But maybe the most provocative detail from our sources connects this ancient melt directly to potential future climate risks.
Ancient methane release, a 2017 study in the Barents Sea.
Right. So scientists found over 100 massive craters on the seafloor. And these are huge. Some are up to 3,000 meters wide.
Underwater mountain-sized craters. They were formed by explosive eruptions of methane.
From methane hydrates.
Exactly. Frozen methane trapped in the sediment. The ice sheets acted like a giant tap, the pressure keeping it stable. When the ice retreated, that pressure was suddenly released.
And it all just blew.
It blew. The researchers described it as like hundreds of champagne bottles being opened simultaneously on the seafloor.
And those areas are still seeping methane today.
They are. And this is where it gets really concerning. The study suggested that there are still other big methane reservoirs down there that could destabilize and erupt again. The LGP retreat was a unique trigger, but warming Arctic oceans today could be another one.
So let's try to synthesize all of this. The last glacial period was so much more than just the Ice Age.
It was a time of global cooling, sure, but with these profound local differences. You know, the Wisconsin in North America, the worm in the Alps. It completely reshaped North America, carving out the Great Lakes, leaving behind those coastal moraines.
Creating the Missoula floods.
Right. In Europe, it was responsible for that whole complex drama of the Baltic Sea's formation. And globally, it set the stage for the megafauna extinctions and the great human migrations. The real power of the LGP wasn't just in the advancing ice, it was in the chaotic, transformative retreat.
And the effects of that retreat, the land still rising, and especially the destabilization of these massive methane stores, they show us that Earth's ancient history is still an active geological force.
Yeah, the instability left behind by the ice over 11,000 years ago is still shaping our world and potentially our future.
Which leaves us with a final provocative thought for you. Given what we know about the explosive release of ancient methane when the last ice sheets retreated, what consequences might the ongoing accelerated deglaciation of our current massive ice sheets in Greenland and Antarctica unlock next?
It's a huge question. It brings geological time right into our present, doesn't it? The forces that were set in motion thousands of years ago are still very much in play.
Thank you for sharing your sources for this deep dive into the last glacial period. We'll catch you next time.